Explanation: a while loop is a control flow statement that repeats a block of code as long as a given condition remains true. The general shape looks like this. While condition then brace body statements that run each iteration, usually update something that moves toward condition becoming false brace. Condition is evaluated before the body runs. If the condition is false the very first time, the body never executes. This is why it is called an entry-controlled loop. Real-world analogy: imagine you are standing at a bus stop and you will keep waiting while the bus has not arrived. As soon as the bus arrives, the condition becomes false and you stop waiting. The key points: the condition must be a Boolean expression. Inside the body, you normally change a variable that appears in the condition. Otherwise, the loop may never stop. The loop may execute 0, 1, or many times. Example: printing numbers 0 to 4. Integer I equals 0. While I is less than 5, then brace print formatted I new line, then I equals I plus 1 comment update moves I toward the false condition brace. A do-while loop is similar to a while loop, but guarantees that the body executes at least once because the condition is checked after the body finishes. Its syntax is do open brace comment body colon statements that run at least once. Comment update variables here as needed close brace while condition semicolon. Real-world analogy: think of a chef who tastes a soup, does a spoonful, then decides while it is still under-salted to add a pinch and taste again. The first taste happens even before the chef knows if more seasoning is needed. The key points: the condition is evaluated after the closing brace. A semicolon follows the while keyword. Because the body runs first, a do-while loop is useful when the initial execution does not depend on the loop condition. It is also entry-controlled in the sense that the loop may continue based on the condition, but it is exit-controlled overall. Example: prompting a user until they type a positive number. Int n semicolon do open brace print enter a positive integer scanf %d comma n close brace while n less than or equal to 0 semicolon. Both while and do while loops repeat a block of code, but they differ in when the loop condition is evaluated. First check while condition is checked before any iteration. Do while condition is checked after the first iteration. 0 iteration possibility: while yes if condition is false initially. Do while no the body always runs at least once. Typical use case: while scenarios where you may not need to run the body at all. For example, iterating over an array whose length could be 0. Do while scenarios where you need an initial action before testing. For example, menu display or input validation that must happen at least once. Real-world analogy: while waiting at a bus stop, while the bus hasn't arrived you may never wait if the bus is already there. Do while tasting soup does a spoonful, then checking if more seasoning is needed you always taste once. Choosing the right loop improves readability and prevents subtle bugs like unintentionally skipping the first required operation. Explanation: a loop invariant is a condition that stays true before and after each iteration of a loop. Proving invariance helps us verify that a loop works correctly and eventually stops. Example: sum of the first n positive integers. We want to compute s equals 1 plus 2 plus n using a while loop. Algorithm: int I equals 1, int sum equals 0. While I is less than or equal to n, sum equals sum plus I equals I plus 1. Invariant: at the start of each iteration, sum equals the sum of numbers from 1 up to I minus 1. Base case: before first iteration, I equals 1, sum equals 0. The sum of numbers from 1 to 0 is indeed 0, invariant holds. Maintenance: assume the invariant holds for some I in the body, we add I to sum, making sum equal to the sum of 1 to I, then we increment I to I plus 1. Now sum equals the sum of numbers up to the new I minus 1. Invariant preserved. Termination: the loop stops when I is greater than n at that moment, I equals n plus 1. By the invariant, sum equals the sum of numbers from 1 to n, hence the algorithm is correct. Mathematically, the invariant can be written as sum equals the sum from k equals 1 to I minus 1 of k. The same reasoning works for a do-while version. The invariant is identical, but we must also show it holds after the first unconditional execution. Why invariance matters? They give a clear, verifiable property that does not change. They guide you to write the correct update statements. They are the backbone of formal correctness proofs taught in algorithm courses. Infinite loops, the condition never becomes false. This usually happens when the loop variable is not updated or is updated incorrectly. Int I equals 0. While I less than 5 open brace comment I never changes arrow infinite loop close brace print quote high newline quote close brace. Fix ensure a clear progression toward the terminating condition. For example, I equals I plus 1. Off by 1 errors. You iterate one step too many or too few. Typical when using less than or equal to versus less than or missetting start or end values. Int I equals 1. While I less than 10 open brace comment wrong colon stops at 9 close brace print format percent d newline, comma, I close brace I equals I plus 1 close brace. Correct version uses while I less than or equal to 10, or start at 0 and use less than 10. Improper variable update strategies. Updating the wrong variable, updating inside a nested conditional only, or updating after a continue statement. Int I equals 0. While I less than 5 open brace if I equals 2 continue semicolon comment skips I plus plus arrow infinite loop. At I equals 2 close brace print format percent d newline comma I close brace I equals I plus 1 close brace. Fix place the update before continue or use a for loop which bundles the update. Best practices. Keep the loop control variable close to the loop header. For example, int I equals 0. Write the update statement as the last line of the body, or in the loop header for loops. Add a comment that explains why the condition will eventually become false. Test edge cases, empty input smallest or largest values to catch off by 1 bugs early. Explanation colon below are 3 classic numeric problems solved with both while and do while loops. Period. The logic is the same semicolon, only the loop form changes. 1 period factorial open parenthesis n factorial close parenthesis. While version int n equals 5 semicolon int result equals 1 semicolon int I equals 1 semicolon while open parenthesis I less than or equal to n close parenthesis open brace result equals result times I semicolon I equals I plus 1 semicolon close brace print open quote percent d exclamation equals percent d backslash and quote comma n comma result semicolon. Do while version int n equals 5 semicolon int result equals 1 semicolon int I equals 1 semicolon do open brace result equals result times I semicolon I equals I plus 1 semicolon close brace while open parenthesis I less than or equal to n close parenthesis semicolon print open quote percent d exclamation equals percent d backslash and quote comma n comma result semicolon. The do while form guarantees the multiplication happens at least once comma which is safe because factorial of 0 is defined as 1 dash you could handle n equals 0 separately if needed. 2 period greatest common divisor open parenthesis Euclidean algorithm close parenthesis. While version int a equals 48 comma b equals 18 semicolon while open parenthesis b not equal to 0 close parenthesis open brace int temp equals b semicolon b equals a modulo b semicolon a equals temp semicolon close brace print open quote gcd equals percent d backslash and quote comma a semicolon. Do while version useful when you know both numbers are non-zero. Int a equals 48 comma b equals 18 semicolon do open brace int temp equals b semicolon b equals a modulo b semicolon a equals temp semicolon close brace while open parenthesis b not equal to 0 close parenthesis semicolon print open quote gcd equals percent d backslash and quote comma semicolon. The loop invariant here is that gcd of a comma b remains unchanged throughout iterations. 3 period series generation dash first n squares. While version int n equals 5 semicolon int I equals 1 semicolon while open parenthesis I less than or equal to n close parenthesis open brace print open quote percent d caret 2 equals percent d backslash and quote comma I times I semicolon I equals I plus 1 semicolon close brace. Do while version int n equals 5 semicolon int I equals 1 semicolon do open brace print open quote percent d caret 2 equals percent d backslash and quote comma I times I semicolon I equals I plus 1 semicolon close brace while open parenthesis I less than or equal to n close parenthesis semicolon. These examples illustrate that the choice between while and do while is often stylistic semicolon. Pick the one that matches the requirement of execute at least once versus maybe 0 times. Explanation: when analyzing algorithms, the time complexity of a loop depends mainly on how many times its body runs. The general rule: if a while or do-while loop runs k times and the body does O of f of n work, the total work is O of k times f of n. In most textbook examples, the loop variable moves linearly. For example, I equals I plus 1, so k is proportional to the input size n, which gives O of n. Examples: 1. Linear scans. I equals 0, while I less than n runs n times constant time work, I equals I plus 1 end while. Complexity equals O of n. 2. Geometric progression having each iteration. While n greater than 0 constant time work, n equals n divided by 2 end while. Number of iterations equals floor of log base 2 of original n plus 1, which is O of log n. 3. Nested while loops quadratic example. I equals 0. While I less than n set j equals 0, while j less than n constant time work, j equals j plus 1 end inner while, I equals I plus 1 end outer while. Outer runs n times, inner runs n times for each outer, giving O of n squared. Do while versus while impact on complexity. The choice does not affect asymptotic complexity because both execute the same number of iterations. The only difference is whether the first iteration is guaranteed. Hence, when you write complexity formulas, treat them identically. Practical tip for algorithm design. Identify the loop invariant to see how many steps are needed to reach termination. Count the updates of the controlling variable. If it grows or shrinks by a constant amount, that yields linear behavior. If it multiplies or divides, that yields logarithmic behavior. If there is another loop inside, multiply the complexities. Understanding these patterns helps you quickly estimate whether a solution will meet time limits in contests or real-world applications. Which statement about a while loop is true? Option A, its body executes at least once. Option B, the loop condition is checked after the body. Option C, the loop may execute 0 times if the condition is initially false. Option D, it cannot be used to read user input. In a do-while loop, the semicolon after the while clause is Option A, optional. Option B, mandatory. Option C, only needed when the condition contains a function call. Option D, replaced by a colon in C++. Explain why an off by 1 error occurs when a programmer writes for I equals 0, I less than or equal to n. Increment I to iterate over an array of size n. Answer: array indices run from 0 to n minus 1. Using less than or equal to n makes the loop access array bracket n bracket, which is one position beyond the last valid element, causing undefined behavior. State the loop invariant for the algorithm that computes the sum of the first n natural numbers using a while loop. Answer: at the start of each iteration, sum equals the sum of all integers from 1 to I minus 1, where I is the current loop counter. Integer I equals 1, prod equals 1. While I less than or equal to 4, multiply prod by I and assign back to prod, then add 2 to I after the loop, print prod as a decimal integer. Trace: start with I equals 1, prod equals 1, condition is true. First iteration, prod becomes 1 times 1 equals 1, I becomes 1 plus 2 equals 3. Second iteration, condition 3 less than or equal to 4 is true, prod becomes 1 times 3 equals 3, I becomes 3 plus 2 equals 5. Third iteration, condition 5 less than or equal to 4 is false, loop ends, printed value is 3. Integer n equals 0. Do block, add 3 to n and assign back to n while n is less than 5, repeat. After the loop, print n as a decimal integer. Answer: first execution makes n equal 3, condition 3 less than 5 is true. Second iteration makes n equal 6, condition 6 less than 5 is false. Loop stops and prints 6.